This lecture is on chemistry, atoms, ions, and molecules. Let's talk about the chemistry of the body. The body is made up of atoms and molecules. Chemical reactions underlie all physiological processes. These include, but are not limited to, growth, movement, heartbeat, digestion, protection from pathogens, water balance, emotions, and many other processes. Two molecules depicted here are serotonin and dopamine, technically the only two things you enjoy. These are neurotransmitters that create the feeling of happiness. Atoms are the smallest unit of matter that makes up an element. Atoms contain a nucleus with positively charged protons, neutrally charged neutrons, and the nucleus is surrounded by energy shells containing negatively charged electrons. Every atom of an element contains the same number of protons. This is the atomic number. Pictured here is sodium, and all atoms within the element of sodium will contain 11 protons in the nucleus. The periodic table of the elements depicts all of the elements found on the Earth as well as atoms that are made artificially. Each section of the periodic table of the element contains a number that depicts the atomic number. There's also a symbol that each element has so that you can recognize the element within a molecular formula. For instance, hydrogen has an atomic number of 1, and the symbol is H. So hydrogen will always be depicted with that symbol of H, and you know that if it is a hydrogen atom, it will have 1 proton in its nucleus. 96% of the body is composed of atoms belonging to these 4 elements: oxygen, carbon, hydrogen, and nitrogen. Oxygen, with the symbol O, makes up 65% of the body. Carbon, with the symbol C, makes up 18.5% of the body. Hydrogen, with the symbol H, makes up 9.5% of the body, and nitrogen, with the symbol N, makes up 3.2% of the body. You can see that there are several other elements that are important in building the body. Their symbols are depicted in the central column, as well as their percentage in the body on the right-hand column. We will talk about a lot of these elements as we go through anatomy and physiology. Isotopes are atoms that have different numbers of neutrons within their nucleus. Radioisotopes contain excess neutrons and release high-energy radiation. Radioisotopes can be used clinically when introduced into the body during medical procedures. This is because radioisotopes are used by cells in a similar manner to regular atoms and can trace metabolic reactions in organs that use these elements. For example, the thyroid gland appears darker in areas where less radioactive iodine is taken up. This can help locate a nodule. In this image, we see several things pictured. We have a normal thyroid on the upper right hand corner. Below that we have, or this is the left hand corner, below that we have a thyroid where too much radioactive iodine is taken up and it glows. This is Graves' disease, which is characterized by an overactive thyroid. We also have nodules pictured. On the left is a hot nodule and the right is a cold nodule. Hot nodules concentrate iodine and are essentially always benign. Cold nodules are usually benign but are sometimes malignant. The majority, perhaps 90% of palpable nodules are cold nodules. Atoms within an element follow the octet rule. The innermost shell is full with 2 electrons. The remaining shells are full with 8 electrons. The outer shell is called the valence shell. This shell must satisfy the octet rule and results in atoms interacting with one another to fulfill the rule. Noble gases are atoms that naturally satisfy the octet rule. Pictured in this image are noble gases, showing the octet rule being satisfied. He is the symbol for helium. This atom has 2 electrons in its valence shell, which happens to be the first shell. Ne is the symbol for neon. Neon has 2 electrons in its innermost shell and 8 electrons in its outermost shell, which is the second shell. The symbol Ar is argon. Argon has 2 electrons in its innermost shell and 8 electrons in its second shell and 8 electrons in its valence shell, which is the third shell. These atoms will not react with other atoms. That is why they occur as gases. Let's talk about ions. An ion is an atom that has gained or lost an electron. A cation is a positively charged ion and is indicated by a plus sign. An anion is a negatively charged ion and is indicated by a minus sign. An ionic bond is an electrostatic attraction between cations and anions. The most famous example of an ionic bond, as illustrated in biology textbooks, is the sodium and chlorine atom. In its natural state, a sodium atom has 2 electrons in its innermost shell, 8 electrons in its second shell, but only 1 electron in its outer shell or valence shell. This makes sodium in its natural state unstable. In its natural state, a chlorine atom will have 2 electrons in its innermost shell, 8 electrons in its second shell, and only 7 electrons in its outermost shell or valence shell. Therefore, chlorine in its natural state is also highly reactive. Sodium is explosive in its natural state. If you put pure sodium in water, it will explode. Chlorine makes a gas, also known as mustard gas. Therefore, these atoms must undergo behaviors to become stable. To do this, the sodium will eject the outermost electron from its valence shell. Now, the sodium is left as an ion, particularly a cation, because it has lost a negatively charged electron and is thus positively charged. The reason for this is sodium has an atomic number of 11, meaning it has 11 protons in its nucleus. After it ejects the outermost electron, it now has 10 electrons. Therefore, having 11 protons and 10 electrons gives it an overall positive charge because protons are positive. When a chlorine becomes stable, it has gained an electron in its outer shell. It is now known as a chloride molecule. The natural state is chlorine, the ionic state is chloride. Chloride is now a negatively charged ion because it has gained a negatively charged electron. Natural chlorine has an atomic number of 17, meaning that it has 17 protons in its nucleus, and it's surrounded by 17 electrons. However, when it gains an electron, it still has 17 protons, but now it has 18 electrons. Protons are positively charged and electrons are negatively charged. So having 17 protons and 18 electrons leaves chloride with an overall negative charge. It is now an anion. These ions will now be attracted to each other through an electrostatic attraction, a positive and a negative charge, like a magnet. When ions are dissolved in solution, they are called electrolytes. The 7 major electrolytes are minerals that are crucial for our bodies to function properly. These electrolytes include potassium, sodium, chloride, magnesium, calcium, phosphate, and bicarbonate, which is a polyatomic ion, meaning that it is a molecule that has an overall positive or negative charge. In this case, it has a negative charge. Potassium is a positively charged ion, so it is a cation, and it regulates heartbeat and neuron transmission. Sodium is also a cation, and it regulates fluid volume and balance and also maintains muscle and nerve function. Sodium and potassium are all oftentimes talked about together in anatomy and physiology. Chloride is an anion, a negatively charged ion. It works with sodium to maintain fluid balance and helps maintain proper acidity in the body. Magnesium, I believe, is a cation and is important in muscle function and heart rate. It also promotes the immune system function and the formation of bones and teeth. Calcium is also a cation, and it is required for new bones and teeth to form. We'll talk about that in the skeleton system. It is also needed for nerve impulses, muscle contraction, and blood clotting. Phosphate is an anion, and it strengthens teeth and bones as well as calcium. It is oftentimes found with calcium in the skeleton as calcium phosphate. It is also important in tissue growth and repair. Like bicarbonate, phosphate is a polyatomic ion, and we'll see it a lot when we talk about the energy molecule ATP. Bicarbonate helps maintain proper acidity. It is used oftentimes as a buffer to neutralize acids in the body. And it is created by the body through breathing, and when it mixes with carbon dioxide in the blood, that's when it forms that important buffer system we'll talk about later. So as you can see, ions are important in maintaining homeostasis and the physiological processes within the body. And you will see all of these electrolytes in our discussions on anatomy and physiology. Now let's talk about molecules and compounds. Molecules are formed when atoms are bonded to one another. Molecules contain the same element. In this instance, the two hydrogen atoms that are linked together are a molecule of hydrogen. Compounds are types of molecules that are composed of different elements. Water, pictured here, is a compound. It's a molecule that contains two different elements, oxygen and hydrogen. Most of the time, we will use molecule when referring to a compound. Molecule is the more standard term. There are two types of compounds. There are ionic compounds mentioned prior that have ionic bonds. So the phosphate ion and the bicarbonate ion. Remember, I said they are polyatomic ions, so that means that they exist as compounds. They have two or more elements bonded together, and they function as compounds that are both negatively charged. The phosphate is negatively charged, and bicarbonate is negatively charged. Then we have molecular compounds. These are compounds that have covalent bonds. Water, pictured here, contains covalently bonded oxygen and hydrogen atoms. So both ionic and molecular compounds are extremely important for physiological processes within the body. The molecular formula indicates the number and type of atoms in a molecule or compound. An example is carbonic acid, depicted as H2CO3. We'll see carbonic acid in the blood when we talk about buffers in a moment with the bicarbonate ion. I'll also show you the bicarbonate ion's molecular formula. But for here, let's talk about what we're seeing in carbonic acid. The H indicates that there's hydrogen, the C indicates that there's carbon, and the O indicates that there's oxygen. The number to the right of the hydrogen indicates how many hydrogens are within this compound. There are two. There's no number to the right of carbon, therefore there's only one carbon within this compound. Oxygen has a number 3 to the right of it, and therefore there are 3 atoms of oxygen. So the molecular formula tells us a lot. It indicates the number of atoms and the type of atoms in a molecule or a compound. The structural formula indicates the arrangement of atoms within the molecule or compound. In this example, we see carbon dioxide, and we have an oxygen, a carbon, and another oxygen. So if we were writing this out as a molecular formula, it would be CO2, But that's not what we're seeing here. We're seeing the structural formula. So we can tell that there are going to be bonds between the oxygen and the carbon, and these lines tell us how many bonds are present. And these lines also indicate that this is a covalently bonded molecule. We'll discuss covalent bonds in a moment. So the structural formula is important because it allows for us to differentiate between isomers. Isomers have the same molecular formula but different structure. So here we see two different versions of glucose. We have alpha glucose and beta glucose. They have the same molecular formula but a different structural formula. We can see that pictured on the right hand side of each molecule. This is very common in the sugar molecules, and you'll see this again when we talk about carbohydrates. Being an isomer gives this molecule a different function. Now let's talk about covalent bonds. Covalent bonds are formed when atoms share two or more valence shell electrons. Carbon, hydrogen, oxygen, and nitrogen are the four most common elements to form covalent bonds in the body. Remember, oxygen is the most abundant, followed by carbon, I believe, hydrogen, and then nitrogen. We can go back here to our table to see. Oxygen, carbon, hydrogen, and nitrogen. Apologies. Should have put those in order. Let's do that. Oxygen, carbon, hydrogen, and nitrogen. This image shows the comparison of an ionic bond to a covalent bond. The ionic bond pictured is sodium and chloride. I told you it's the most famous example of an ionic bond. So the sodium and chloride, anion and cation, so sodium cation and chloride anion, are attracted to each other through electrostatic charges. However, in a covalent bond, what occurs is this hydrogen has one proton, remember, and it also has one electron in its outer shell. This makes hydrogen very reactive. It needs two electrons in order to be stable. Sometimes the hydrogen will eject this electron and exist as just a proton, and it will be indicated with a positive sign, H+. It can still form covalent bonds, though, which is pretty radical. But in this case, when we see this illustration, the hydrogen still has its electron, and it can bond to another hydrogen over here through a covalent bond. So what they're doing is they're actually physically linked together through their sharing of electrons. So as these electrons are moving around in the orbitals, they are sharing equal time between both of these hydrogen atoms in this molecule. It's important to note that there are two types of covalent bonds. There's polar and nonpolar. So polar molecules are formed when covalent bonds have unequal sharing of electrons. Polar molecules interact with water, Polar molecules contain electronegative atoms. Electronegative atoms are located on the upper right-hand side of the periodic table of elements. And they are going to attract most of the electrons in the molecule. This is what gives the molecule polarity. So here, in this polar covalent bond, we see that we have a chloride that is bonded to a hydrogen. So in this case, they are covalently bonded. They will be sharing their electrons. This is not an ionic bond. However, chloride, being the larger and the more electronegative, will contain electrons most of the time and will have an overall positively negative charge. That's what that indicates, a partial negative. Hydrogen, if you recall, is the first element in the periodic table. It is not electronegative. I told you prior that hydrogen will sometimes even just kick its electron off and exist as a naked proton. So therefore, hydrogen is usually going to be indicated with this partially positive charge here in a polar covalent bond. So this is extremely important because with it being able to interact with water, it can also interact with ions and other charged molecules. Nonpolar molecules occur when covalent bonds have an equal sharing of electrons. Nonpolar molecules are generally insoluble in water. Here we see two chloride ions bonded together, and since they have both equal sharing of electrons, they are nonpolar. So in this case, the chlorides will not be soluble in water. So these are the three types of bonds we've talked about so far: the nonpolar covalent bond, the polar covalent bond, and the ionic bond. Here's the periodic table of the elements again, and this is showing us the atoms that are most likely to be electronegative. The two that we will see the most in anatomy and physiology are the nitrogens and the oxygens. Because remember, oxygen is the most abundant element in the body, and nitrogen is the fourth most abundant element in the body. Some molecules are amphipathic, meaning they have polar and nonpolar regions. The polar regions can interact with water. The nonpolar regions do not interact with water. One of the most important amphipathic molecules that we'll talk about in anatomy and physiology is the phospholipid. The phospholipid contains a polar head with the phosphate. Recall that phosphate is a polyatomic ion with a negative charge. Being an ion, it can interact with water. The lipid portion of a phospholipid contains fatty acids. Fatty acids are nonpolar, therefore they do not react with water. The part of the amphipathic molecule that interacts with water is hydrophilic. Hydro meaning water, and philic is love. The nonpolar portion of an amphipathic molecule is hydrophobic. Again, hydro is water, and phobic is fear. This illustration shows three arrangements of phospholipids in different media. At the top, we see that the phospholipids are arranged in one layer. The hydrophilic polar heads in red are on the side of the media where water occurs, and the fatty acid nonpolar hydrophobic tails are interacting with the oil. So that is how the amphipathic molecules interact with water and oil. The hydrophilic heads will face the water. The hydrophobic tails will face the oil. This next illustration shows a monolayer, meaning one-layered bubble. This occurs in the body in the form of what we call micelles, which help to transport fat through the blood. And this is convenient because the blood is mostly water. And if we want to transport fat through the blood, fat cannot interact with water, so we surround it in a layer of amphipathic phospholipid molecules. Therefore, the hydrophilic polar heads can interact with the blood, and the hydrophobic fatty acid tails can interact with the oil, the fat, and transport it throughout the body. Now let's look at a more complex arrangement of phospholipids. This is what the basic structure of all cell membranes is composed of. This is called the bilayer because it has two layers. The body is mostly water, hence the oxygen and the hydrogen. Water is a polar substance. Therefore, water will interact with ions and other polar substances, but it will not interact with nonpolar substances. Notice that oil and water don't mix. It's for that very reason. Cells live in an aqueous or watery environment. And so in order to exist in this watery environment, it is going to be surrounded by a phospholipid bilayer. The polar heads will face the water, and the nonpolar tails will be interior, away from the water. Now we have one more problem. Not only do cells live in water, but cells are mostly made of water. So in order to facilitate this, there is another layer of phospholipids where the polar heads face the intracellular water within the cell, and again, the nonpolar tails are facing away from the water. So what we have created here is this shell, basically, where the outer and inner layer can interact with water, and the interior lipid layer is protected from the water. So not only does this form a sphere that gives the cells its shape, but as we'll talk about in the cellular chapter, it also makes the cell selectively permeable and determines how the cell will interact with substances in its environment. So stay tuned. I hope that you're starting to see the importance of chemistry in anatomy and physiology, and how these atoms and molecules are building the body and also maintaining homeostasis through physiological processes. All right, let's talk about the third type of bond. We've talked about ionic bonds and covalent bonds, and now let's talk about hydrogen bonds. So hydrogen bonds occur between an electronegative atom in one molecule and an electropositive atom in another molecule. Therefore, the molecules that will be interacting with each other will be polar. Individual hydrogen bonds are weak. However, when they occur in large numbers, they play an important role in water tension, protein structure, and nucleotide structure. We'll talk about all of those in this chapter. This is a molecule of water. Recall that water is polar. I'll elaborate on that soon. But this is a good illustration because it shows that the oxygen is the electronegative atom in the water molecule. Is that partial negative charge. And the hydrogens are the electropositive atoms in this molecule, shown by the partial positive charges. So the way a hydrogen bond works is the hydrogens of this water molecule will be attracted to oxygens of other water molecules. Hydrogen bonds are indicated by a dashed line showing that they are a weak bond that can be made and broken very quickly. They're like an electrostatic interaction seen in an ionic bond, only not quite as strong. All right, now let's start putting all of this together and looking at molecules that are going to be found within our body. So inorganic molecules do not contain both carbon and hydrogen. Some inorganic molecules contain neither of these elements. They won't have carbon or hydrogen. Inorganic molecules can be molecular compounds or ionic compounds. Important inorganic molecules in the body are water, salts, acids, bases, and gases such as oxygen and carbon dioxide. Just a quick disclaimer about acids and bases. Not all acids and bases are inorganic. Organic molecules consist of groups of carbon atoms bonded to hydrogen. So they will have both carbon and hydrogen, and they are molecular compounds bonded by covalent bonds. Organic molecules will form the carbohydrates, lipids, proteins, and nucleic acids. So notice that we see the term acids here already. So sometimes acids can be organic if they contain both carbon and hydrogen. Proteins are composed of amino acids, so they will have an organic acid and an organic base. But the reason that acids and bases are listed here under the important inorganic molecules is that they can also occur as inorganic molecules. Acids and bases will be defined soon. So they're not based on whether they are organic or inorganic. They're based on other behaviors. All right, so let's move through these inorganic and organic compounds. First, we're going to talk about water. Water is an inorganic compound, and it is the most important and abundant molecule in the body. Water is composed of one oxygen and two hydrogen atoms, and it has a molecular formula of H2O. As mentioned before, water has a polar covalent bond. The oxygen is electronegative and will attract the X electrons, and is indicated here with a partial negative charge. The hydrogens will be electropositive and will not attract electrons, and so they are indicated here by the partial positive charge. The polarity of water makes it the universal solvent. Let's define some terms. A solution is made of solutes, which are the substances, and the solvent, which is the liquid. So basically, in order to form a solution, you have to add together the solutes and the solvent. Due to its polar nature, meaning the electronegative oxygen and the electropositive hydrogen, water is the universal solvent. We even saw that as long as amphipathic molecules are in the solution, water can interact with fats. That's a process called emulsification. Anyway, water can dissolve any ion or polar molecule, and it does this by forming hydration shells around the solutes. The sodium and chloride are shown surrounded by water molecules. Imagine that this would be an entire sphere around these particular ions. In order for the water to interact with the chloride ion, the partially positive hydrogens will interact with it. Because remember, we have opposites attracting. In order for water to interact with the positively charged sodium cation, these partially negative oxygens will surround the sodium. So many water molecules will surround each of these atoms that it will pull them apart from each other, and the salt will be dissolved in the water. Water molecules exhibit cohesion. They can form hydrogen bonds with other water molecules. This is picturing cohesion, where the two water molecules are joined together. It would be better if the author of the illustrator had an arm coming out of a hydrogen, correct? Because we know that that's what would form that cohesive unit, would be the hydrogen bonding to the oxygen through the hydrogen bond. You're smart enough to have picked that up now, haven't you? Water molecules can also exhibit adhesion, meaning water molecules can form hydrogen bonds to other surfaces. This allows them to stick to surfaces. You see this when water beads up on surfaces. This is important in moving substances through our bodies. Water also lubricates and cushions our joints, our body membranes, such as the serous membranes, our eyes, our organs, our tissue fluids, and our cells. Water also helps blood move through vessels and maintain blood pressure, partly because of that cohesive and adhesive action mentioned prior. Water has a high specific heat. It takes a lot of energy to raise the temperature of water. Thus, water maintains a relatively stable body temperature. Water also has a high heat of vaporization. It takes a lot of energy to turn liquid water into gaseous water. This aids in evaporative cooling, which carries heat away as the sweat evaporates. In this illustration, we see that the body is overheating, and thus we're going to engage homeostatic feedback mechanisms to cool the body down. So the water in the blood will carry heat to the skin. The heat will then radiate through the skin. We will also be sweating. As the sweat evaporates, the water molecules will carry the heat away. This will then cool the skin and cool the body core, returning us to homeostatic set point of 98.6 degrees. Water is also important in chemical reactions. There are two types of chemical reactions that we will see that will make or break covalent bonds. Dehydration synthesis will occur when large molecules are built by the removal of water. Hydrolysis will occur when large molecules are broken apart by the addition of water. In the body, this occurs through the use of enzymes, but in a solution outside of the body, generally adding heat will cause dehydration synthesis and hydrolysis to occur. This picture illustrates dehydration synthesis of sugar molecules. This H and this OH, so hydrogen and hydroxide, if they are put together, they will form water. This is how your liver will build glycogen. The glucose molecules will go to your liver that aren't needed for energy, and enzymes in the liver will remove the hydrogen from one glucose and the hydroxide from another glucose, making water. And also in the process, it joins these two glucose monomers together. Ultimately, as the liver continues to add more glucose monomers to this growing glycogen chain, we can store sugar for later use. Let's say we are hungry and we need to release some of this sugar back into our bloodstream. Enzymes in the liver will take water molecules and add them back between these two glucose monomers in the glycogen chain. By doing so, we will break a glycogen off of the glycogen chain, or glucose, and return it into the bloodstream. Okay. When we talk about acids and bases in this part of the discussion, we will be looking at them from an inorganic molecule perspective. So certain electrolytes will influence the pH of a solution. Acids are electrolytes that donate hydrogen cations in a solution. So remember, I told you that acids are not going to be defined by whether they are organic or inorganic. They are defined by their behavior. And in this case, the acid is behaving in that it is donating hydrogen cations into a solution. And by doing this, the acids are going to lower the pH of the solution. So yes, if you put pure hydrogen into a solution, all of those hydrogen ions will lower the pH and make it acidic. Bases are electrolytes that donate hydroxide ions into solution. Bases also accept hydrogen ions. That means that they will bond them to themselves when building a molecule. So bicarbonate mentioned earlier will accept hydrogen ions. This raises the pH of solution. Salts are different than acids and bases because they do not influence the pH of a solution. They do not contain hydrogen or hydroxide ions. So when we looked at sodium chloride earlier, that is a salt because it contains sodium and chloride. Notice there's no hydrogen or hydroxide within the sodium chloride molecule. So they're neutral. The pH scale records the amount of hydrogen ions in a solution. It is an inverse scale. Therefore, the more hydrogen ions in the solution, the lower the pH. And the lower the pH, the more acidic the solution will be. The scale exists from 0 to 14. 0 is the most acidic. It has the most hydrogen ions that it can possibly have. A pH of 7 is neutral. The hydrogen ions will equal the hydroxide ions, and we've learned that hydrogen and hydroxide together will make water. So this will be like pure water. It may have salt in it, like sodium chloride, but remember, sodium and chloride do not influence the pH of the solution. 14 is the most basic or alkaline pH, and it means it has a greater number of hydroxide ions. This illustration shows the pH scale. Acids are generally indicated by red because the litmus test, the strip will turn red in the presence of an acid. Bases are usually illustrated by dark blue because on the litmus test, when the strip is introduced to a base, it will turn dark blue. And neutral here is somewhat in the middle. Generally on a litmus test, from what I remember, neutrals generally show up as green, but this illustrator chose to blend them together and form a light purple. Seawater can occur at a pH of 7, so it can be neutral if it has, just the salt water in it, but if it has other substances, it can become more basic. Blood is slightly basic at a pH of 7.4. Hydrochloric acid has a pH of 0. So when this dissolves in solution, it will completely dissociate into a hydrogen ion and a chloride ion. This is a solution that we see in our stomach acid. These hydrogen ions are so reactive that they cut through proteins and fats like little molecular knives. And this is how the hydrochloric acid dissolves the foods that we eat. On the opposite side of the scale, we have sodium hydroxide with a pH of 14. When sodium hydroxide is dissolved in solution, it will completely disassociate into sodium ions and hydroxide ions. Both extreme acids and bases can disrupt molecular bonds between molecules. Let's look at acids in more detail. Acids lower the pH of solution by donating hydrogen ions. Strong acids dissolve completely and release all of their hydrogen ions into solution. Hydrochloric acid and gastric juice breaks down food substances. Weak acids do not dissolve completely in solution. Carbonic acid forms when carbon dioxide and water mixes into the blood and tissue fluids. Another type of strong acid, hydrofluoric acid, looks like it's found in batteries, and it has the pH of 0, which is the most red. So notice as we approach the neutral, we get to green, as mentioned earlier. So the pH of 6 here is shown in a light green. So cow's milk will be slightly acidic, and it says that milk goes sour over time due to the bacteria producing lactic acid as a part of the fermentation process. Bases raise the pH of solution by releasing hydroxide ions or accepting hydrogen ions. Strong bases dissolve completely and release all of their hydroxide ions into solution. Sodium hydroxide is called lye, and it is corrosive to all body tissues. Weak bases release some hydroxide ions or accept some hydrogen ions. Bicarbonate, here you see the molecular formula finally for our bicarbonate ion, HCO3 negative. Bicarbonate helps neutralize carbonic acid in the blood and tissue fluids. So we'll see bicarbonate and carbonic acid in a buffer solution in the coming slides. Here's distilled water, a pH of 7. See how it's green there. And then as we become more basic, more alkaline, we become dark blue to dark purple. So here we see the caustic soda known as sodium hydroxide. In its purest form, it is a white solid and can cause severe burns to its high alkalinity. So remember, as we go towards the opposite ends of the pH scale, we become more corrosive to molecules. So a very acidic or very alkaline substance can both affect body tissues. And so this can spell trouble in the body. Thus, buffer systems will regulate pH by neutralizing the acids and bases. Buffer systems usually consist of weak acids and weak bases that react to produce water and salt. Examples include the regulation of blood pH. So the set point of human blood must remain in the range of 7.35 to 7.45. The respiratory and urinary systems combine carbonic acid and bicarbonate to keep blood within the set range. Carbonic acid is a weak acid and bicarbonate is a weak base. So let's look at the reaction here. When carbon dioxide mixes with water in the blood, it forms carbonic acid, H2CO3. Carbonic acid is a weak acid. It will not completely dissociate in the blood. It will not donate all of its hydrogen ions. It will only donate one. And so here we see that one hydrogen ion being donated into the blood. So a lot of carbonic acid, however, will lower the pH of the blood and make it more acidic. So thus, the bicarbonate ion that is also formed from the dissociation of carbonic acid can then bind and accept that hydrogen back and form carbonic acid if the pH then raises too high. So we see carbonic acid and the bicarbonate ion constantly forming and breaking as the pH fluctuates between that 7.35 and 7.45. The lungs will help to buffer that by breathing out carbon dioxide. As we breathe out carbon dioxide, we're getting rid of the source of the carbonic acid. Thus, by breathing out carbon dioxide, we help to raise our blood pH. If we hold in our carbon dioxide, we will lower our blood pH. The kidneys also help by reabsorbing or secreting hydrogen and bicarbonate ions. So if our pH is getting too high, then the kidneys will reabsorb hydrogen ions, and we may urinate out bicarbonate ions. If our pH is becoming too low, our kidneys will do the opposite. We will urinate out hydrogen ions and we will reabsorb bicarbonate ions. So this is a physiological homeostatic feedback loop that is maintaining our set point of blood pH at 7.35 to 7.45. And the systems that are working together to do this are the respiratory system and the urinary system. When the pH falls below 7.35, a disease results, and it's called acidosis. There are two types of acidosis based on whether the lungs or the kidneys are affected. Respiratory acidosis occurs when the patient cannot breathe out. Because they cannot breathe out their carbon dioxide, the carbon dioxide is building up in their bloodstream and forming carbonic acid. Symptoms of respiratory acidosis include hypoxia, hypoventilation, meaning they can't breathe out, drowsiness, muscle weakness, a lowered blood pressure, dyspnea, meaning trouble breathing, headache, hyperkalemia, meaning too much sodium building up, and dysarrhythmias, meaning that we're having an elevated calcium or potassium. So I think hyperkalemia is potassium. My apologies. Another thing that can occur is a loss of consciousness. Metabolic acidosis occurs when the kidneys are not able to excrete the acids or conserve the base. So the kidneys cannot get rid of hydrogen and they cannot reabsorb bicarbonate. A major component that can lead to metabolic acidosis is diabetes. It can lead to a diabetic coma, renal failure, and shock. Symptoms are very similar to respiratory acidosis: headache, decreased blood pressure, hyperkalemia, muscle weakness and twitching, vasodilation, which is noted here, so we have warm flushed skin, nausea, confusion, and you're going to hyperventilate because your lungs are going to try to compensate by getting rid of carbon dioxide to help raise the pH of your blood. When pH rises above 7.45, the disease that results is alkalosis. Again, there are two types of alkalosis. There's respiratory alkalosis and metabolic alkalosis. Alkalosis is not as common as acidosis. Respiratory alkalosis can be caused by hyperventilation seen in anxiety. And as the blood pH rises. Symptoms are seizures, deep, rapid breathing, elevated heart rate, low or normal blood pressure, hypokalemia, so you're losing the potassium in your blood, numbness, confusion, lightheadedness, nausea, and vomiting. This can lead to heart attack as well, hence the tachycardia and seizures. Metabolic alkalosis can occur from overuse of antacids, severe vomiting, excessive GI suctioning, use of diuretics. Symptoms of metabolic acidosis include restlessness, tachycardia, compensatory hypoventilation, so your lungs are trying to keep carbon dioxide in your blood, confusion, nausea, vomiting, and diarrhea, tremors, and hypokalemia. So in metabolic acidosis, the kidneys, or metabolic alkalosis, the kidneys are not able to reabsorb enough hydrogen ions, and they're reabsorbing too many bicarbonate ions, and the pH elevates. So respiratory alkalosis and metabolic alkalosis can lead to heart attack. Respiratory acidosis and metabolic acidosis can lead to a loss of consciousness and a coma. Thus, we must maintain the pH of human blood within our set range of 7.35 to 7.45. And this is maintained by buffer systems to keep our acids and bases in balance. Okay, we'll finish out the chapter discussing biological macromolecules. Biological macromolecules are the large organic molecules that form the structures of the body. They include lipids, carbohydrates, nucleic acids, and proteins. These biological macromolecules always contain carbon, hydrogen, and oxygen. Some biological macromolecules may also have nitrogen, phosphorus, or sulfur. Carbon is the backbone of biological macromolecules. It can form covalent bonds with up to 4 other elements at the same time. This is because of the valence shell electrons. Carbon has 4 valence shell electrons. Carbon atoms commonly bond to other carbon atoms, forming chains and rings. So here we can see a straight chain, branch chain, and a ring. The lines depict that these are covalent bonds, and the number of lines depict the number of electrons shared in this covalent bond. So a single line is 1 pair of electrons. 2 lines indicate 2 pairs of electrons, known as a double covalent bond. Biological molecules consist of polymers, which are molecules made of monomers, or repeating subunits. Lipids contain fatty acid monomers. Carbohydrates contain monosaccharide monomers. Nucleic acids contain nucleotide monomers. And proteins contain amino acid monomers. Polymers are built through dehydration synthesis and are broken into monomers through hydrolysis. Lipids are a diverse group of compounds made up of fatty acid monomers. Fatty acids are nonpolar and hydrophobic, meaning they are insoluble in water. 3 major lipids in the body are triglycerides, phospholipids, and sterols.
Pictured here is the triglycerides with 3 fatty acid chains. Phospholipids, the amphipathic molecule mentioned prior with a phosphate group and 2 fatty acid chains. And a sterol, which has 4 fused hydrocarbon rings. And this makes the sterols waxy. Triglycerides are the most abundant lipid in the body. They are commonly referred to as fat. They are the major fuel source for the body, and they contain saturated and unsaturated fatty acids. The triglyceride consists of a glycerol head and 3 fatty acid chains. If the fatty acid chain is kinked, it is unsaturated because it has a double covalent bond. If the fatty acid is saturated, it is straight because it only contains single covalent bonds. Triglycerides are stored in adipose tissue, which contains our adipocytes or fat cells. So a fatty acid is saturated if it contains single covalent bonds between the carbon atoms. An unsaturated fatty acid contains double bonds. There are 2 types of unsaturated fatty acids. Monounsaturated fatty acids contain 1 double bond. Polyunsaturated fatty acids contain more than 1 double bond. Pictured with the saturated fatty acid, we can see that the single covalent bonds create this linear chain, whereas in a monounsaturated fat we have 1 kink that bends the chain, and then in a polyunsaturated fat with our numerous kinks we can actually start to see curvatures occur. Monounsaturated and polyunsaturated fats are healthy for you, and they include oils. These help to decrease inflammation in our bodies and can decrease the risk of heart disease. Saturated and trans fats do the opposite. They increase inflammation in our bodies and can increase the risk of heart disease. So we see saturated fats in our animal fats, as well as vegetable fats such as coconut and palm oil. Trans fats are vegetable oils that have been transferred from unsaturated fats into saturated fats. And they do that by removing the kink out of the fatty acid tail, thus straightening it. Trans fats are useful when making cakes and pastries, chocolate, fried foods, and our fast foods. So they behave just like saturated fatty acids when introduced into our bodies. Here is an image of the body's fuel tanks. Adipose tissue can store the most fuel. Adipose tissue can grow. It can hypertrophy, meaning grow, in its numbers of cells and the sizes of those cells. So as the fatty acid or the fat fills the cells will then undergo mitosis and duplicate their numbers in order to store more fat. The other body fuel tanks are going to store sugar. So the glycogen in the liver can only store so much sugar, about 300 calories worth. Once the liver is full of glycogen, then insulin will convert the remaining blood glucose into fat. Blood glucose itself can only contain about 40 calories of energy at a given time. Muscles store their own sugar and fat stores. Generally, however, it is for use by muscles only. It doesn't share it with the rest of the body because muscles are one of the most energetically expensive tissues to maintain. And that's why if you build muscle mass, you tend to burn fat because the muscles are going to need to store that fat, and they're also going to need to use the sugar that you are ingesting to maintain their metabolism. The second type of fat is the phospholipid. Phospholipids make up the essential structure of cell membranes. As mentioned before, it's because they are amphipathic. The phosphorus is hydrophilic, and the fatty acids are hydrophobic. So the extracellular fluid will be mostly water, and the intracellular fluid will be mostly water. Sterols are waxy, and they include cholesterol. Cholesterol is the most important sterol in the body, and its functions include stabilizing cell membranes. It's a component of bile salts, which emulsify fats in the digestive system. And it's a component of steroid hormones such as estrogen, progesterone, and testosterone. HDL and LDL cholesterol transport triglycerides throughout the body through those micelles that I mentioned earlier. HDL means high-density lipoprotein. It means that it's going to have more proteins than lipids. It's what we call the good HDL. It regulates the storage of cholesterol and it promotes excretion of cholesterol. So it's moving it out of the body. The LDL stands for low-density lipoproteins, meaning that it has a lot of fat in it and less protein. Therefore, it is what stores cholesterol in the bloodstream and is known as the bad cholesterol. The reason that LDL leads to heart disease is because it sticks to the walls of your arteries and forms the plaques. Dietary cholesterol is a factor, however, the most important factor in your blood cholesterol levels from dietary perspective comes from saturated and trans fatty acid consumption. This is the National Cholesterol Education Program cholesterol guidelines. The green is the desirable range. Your blood cholesterol should be less than 200. Your LDL should be less than 130. Your HDL should be 50 or higher, and your triglycerides should be less than 200. A lot of our high cholesterol does come from our dietary consumptions of trans and saturated fatty acids. Some folks are unlucky, though, and have a genetic predisposition to having high cholesterol. Tips for a healthy heart. If you're a smoker, stop smoking. Drink less. The FDA guidelines are 1 alcoholic beverage a day for females and 2 for males. And mind you, an alcoholic beverage is 4 ounces of wine or like 1 can of beer. It's a lot lower than what we would normally consider to be quote unquote one drink. So drink less if you can. Reduce your stress if you can. Ditch the salt. You don't need to salt everything, and try to stay away from all those processed foods as best as you can. And if you do eat processed foods, read the sodium labels. Also, cut the fat. Try to eat more plant-based diet. It's not only better for the environment of the earth, but it's better for your body's environment. You can still eat fat, obviously. We need it. We need meats and stuff. However, we need more vegetables than anything, really. Eat your veggies, guys. Veggies are the awesomest. Get active. Get out there and play with your kids, walk your dog, do a couple of squats. That will also help reduce your stress, and it'll help you lose weight, which will help you lower your blood pressure. Also, sleep comes from reduced stress and more activity and a better diet. Sometimes I eat way too much at night before I go to bed, and I can't sleep very well. So all of this comes together to make for a healthy heart. Moderation is the key. Another type of fat that's important in the body is the eicosanoids. So these are modified 20-carbon fatty acids. They are synthesized from arachidonic acid, and their primary functions in inflammatory response and nervous system communication. There are 4 classes: the prostaglandins, prostacyclins, thromboxanes, and leukotrienes. The next biological macromolecule is the carbohydrates. Carbohydrates consist of monosaccharides. That means one sugar. Saccharin is sugar and mono is one. So the monomers are called monosaccharides, and they contain carbon, hydrogen, and oxygen in a 1-to-1 ratio. So we'll see it written as like C6H12O6, and that N would be a 6. There are also 5 carbon sugars, and so that would be 5, C5H10O5. Carbohydrates are polar, therefore they interact with water, and their functions are a major source of cellular fuel, cellular communication, and they are the sugar components of DNA and RNA. I mentioned prior that carbohydrates are very important as far as isomers are concerned. So here are the 3 monomers of carbohydrates: glucose, galactose, and fructose. They all have the molecular formula of C6H12O6. However, they have different structural formulas. This gives them different properties. Glucose is the only one that our cells can directly use in energy metabolism. Therefore, the liver has to convert the other monosaccharides, galactose and fructose, into glucose in order for them to be used as cellular energy. When we eat sugars or foods that contain high levels of fructose, you can tell by looking at the ingredients. It says high fructose corn syrup. Fructose is the sweetest of the monosaccharides, and that is why companies will put the fructose into the processed foods to make them sweeter. Fructose in itself isn't that bad for you. As you can see, if we put a fructose and a glucose together, we get the table sugar, which is sucrose, which is nice and sweet. The problem arises when we get too much fructose. Our liver cannot process it into glucose for energy, and thus the body will end up storing it as fat. Again, the most important monosaccharide in the body is glucose. It is a major source of cellular fluid or fuel, and it is the only source of fuel for the brain. So cells can also get their energy from fatty acid metabolism, but the brain cannot. The brain can only use glucose to make energy. Glucose is stored as the polysaccharide called glycogen in both the liver and the muscles. This illustration shows through the process of dehydration synthesis, enzymes can remove a water from between 2 glucose monomers, thus joining them together and forming glycogen. Diabetes is a growing concern for people not only in America but across the world. And it's reaching critical levels here in our country. A1C scores help to indicate blood glucose levels. So a healthy H1C test score should be 6 or below. Good is between 7 and 8. Actions suggested when it rises above 9. Nucleic acids are composed of nucleotide monomers. Nucleotide monomers contain a phosphate group, a pentose sugar, and a nitrogen-containing base. The major nucleic acids in the body are ATP, DNA, and RNA. This illustration shows the structure of a nucleic acid. We have our phosphate group, our polar polyatomic ion. We also have a sugar. This is a 5-carbon sugar, so it's a pentose sugar. Glucose is a 6-carbon sugar. So this is different than glucose. And we have our nitrogenous base, meaning that it will have like a basic type of behavior in the body. It's also going to be important when we talk about amino acids later. ATP, or adenosine triphosphate, is a nucleotide containing a ribose sugar, a nitrogenous base, and 3 phosphate groups. ATP is the primary energy molecule of the body. Carbohydrates, lipids, and proteins contribute to the formation of ATP, particularly glucose, fatty acids, and amino acids. We'll talk about ATP a lot throughout anatomy and physiology, particularly starting with the next chapter on energy metabolism. ATP powers the movements of molecules in the body, particularly protein pumps, muscles, and motor proteins. In this first illustration, we see the sodium-potassium pump. Remember how I said sodium and potassium are going to be seen together throughout the course of this study? In order to power a pump that maintains electrolyte concentrations around the cell membrane, the ATP will donate its terminal phosphate group, changing the shape of our pump, opening it to the outside. When it's time to open the pump to the inside, the terminal phosphate will be removed from the pump, and that opens the pump to the inside. Once we have removed the terminal phosphate from ATP, it is no longer ATP. It is now a molecule called ADP, adenosine diphosphate. The reason that we need carbohydrates, fatty acids, and proteins to regenerate our ATP is because those will power cellular respiration that helps join another terminal phosphate to our ADP and regenerate ATP for use in other parts of the body. Another protein that ATP moves is the myosin in a muscle. All these little heads have to move in order to contract our muscle. And so ATP will act in a similar way as seen here. Well, it will donate its terminal phosphate and cause the myosin heads to move and walk the actin towards the center of this sarcomere, which is the contractile unit of a muscle, shortening our muscles and generating force. Here we see motor proteins called kinesins. They have little feet on them just like the myosins. And as we saw up here in this illustration, ATP will go in and it will donate that terminal phosphate to the feet, and by doing that, it will power the energy to change the shape of that protein. And then the removal of that phosphate will change the shape once more. And so by adding and removing phosphates to these proteins, the ATP moves these proteins, and we can get a lot of work done in the cells of our body. Now let's talk about DNA. DNA is a double-stranded molecule. It contains a deoxyribose sugar, a phosphate, and one of 4 nitrogenous bases. The nitrogenous bases are adenine, thymine, cytosine, and guanine. Adenine will pair with thymine. Cytosine will pair with guanine. I like to remember A and T is where it's at. And then C and G, they're both curved. And there's also a vitamin store called GNC. That's how I remember that. Nitrogenous bases are arranged in triplets. Each triplet codes for an amino acid that will be used to build a protein. RNA is a single-stranded family of molecules. It contains a ribose sugar, a phosphate, and one of 4 nitrogenous bases. So adenine will pair with uracil instead of thymine. There's no thymine in RNA. Cytosine will pair with guanine. And RNA molecules will carry out DNA's instructions for synthesizing the proteins. So basically, RNA will copy the triplets of the DNA and carry it out into the cell to make proteins. We will talk about that in the cell chapter. This shows the ribose sugar versus deoxyribose sugar. So ribose has an oxygen contained to the hydroxide here. A deoxyribose does not contain the hydrogen, the oxygen. It just has a hydrogen. So that's what the word ribose versus deoxyribose indicates. And that's one of the big differences between RNA and DNA. Another difference is the nitrogenous bases in RNA will either be adenine, cytosine, guanine, or uracil. And in DNA, there will be adenine, cytosine, guanine, or thymine. Our last biological monomer and last few slides of our chapter will focus on proteins. So proteins contain amino acids in a specific polypeptide sequence. So again, we have the amino group, which will act as a base, and the acid group that will act as an acid, and in this case, they are organic acids and bases. So there are 20 amino acids that make up an endless variety of proteins. Each amino acid will be coded for by the triplets in the DNA. Amino acids are joined by special covalent bonds called peptide bonds. Thus, we call a growing protein a polypeptide. There are 4 structures when building proteins. The first is the primary structure, or the polypeptide bond. And this is the structure that is coded for by the DNA triplets. So each of these amino acids in the polypeptide chain was coded for by a triplet in the DNA. Based on the behavior of the amino acids, these polypeptide chains will start to coil or bend. If they're coiling, they become an alpha helix. If they bend, they become a beta sheet. A polypeptide sequence will do both. it will both coil and bend. Thus, once that occurs, we have formed the next structure of our protein called a tertiary structure. And finally, in order to make a functional protein, most of the time, 2 or more tertiary structures will bond together from different polypeptide chains. And that will make the quaternary structure and the functional protein. So proteins will be based on structure. There'll be fibrous proteins, which are strand-like, globular proteins, which are rounded in a globe, or intermediate between fibrous and globular. They will be classified based on their composition, so they will be simple or conjugated, so, tertiary or, quaternary. And then we'll have classification based on functions. They will be structural proteins, enzymes, hormones, pigments, transport proteins, contractile proteins like your muscle cells, storage proteins. They can even act as toxins. And this is the amino acid structure. The amino group contains nitrogen. That's what amino means. And that's the nitrogenous base. So all of these here, nitrogenous base, like adenine, cytosine, guanine, and uracil, they also will contain nitrogen. And then we have the acid, which is going to contain COOH. I like to think of it as COO. So that's our amino and our acid group. The way that they join together is the acid group of one amino acid will join to the nitrogenous base of another amino acid. So that's where the peptide bonds come in. And then this R group here is going to be unique to the particular amino acid. There are 20 amino acids, and thus there will be 20 different R groups. So here are the 20 amino acids. If they have a solid line, it means that they are non-essential. We make those in our body. If they have a dotted line, it means that they are essential. We cannot make those in our body, and we must eat them in our diet. If they are red or green or orange or blue or pink or yellow or blue, dark blue, they have different functions. And so this is why amino acids can have behaviors to bend and coil and twist and join particular polypeptide chains in such a way as to make the protein. And it's another reason why proteins can have so many functions, because with all of these behaviors of the amino acids, proteins can act as enzymes, as mentioned, structural proteins, hormones, toxins, transport proteins, etc. So protein form and function is endless, and that's one of the big things that builds these biological molecules in all the different varieties that we see on planet Earth. And they're coded for by the triplets found in DNA. And that's why DNA codes for the structures of life, and the proteins are those structures. So when we saw like fats and carbohydrates, they have important structures and functions as well, but in a lot of cases we saw that fats and carbohydrates are largely used for energy to power these proteins. So proteins are the foundation of the multicellular body plan. Collagen, the most abundant protein in animals, holds cells together. Other functions of proteins include, but are not limited to, skeletal structure, movement, enzymes, antibodies, transport, hormones, neurotransmitters, and pigments. The reason I have a picture of a lady looking at herself in the mirror is because, pardon my voice here, is because when she looks at herself in the mirror, she's seeing the accumulation of all of her proteins. Here's a picture of what's called a ghost heart. This is showing the collagen framework. Remember I said collagen is the most abundant structural protein in the body. It basically builds the foundation of our body. If we remove all the cells within all the tissues of our bodies, only the collagen will remain. And you can see every single feature in the structure of the heart based on this collagenous framework. We stop producing collagen as we get older, and this is one of the reasons why we age and our skin and other body tissues start to break down. That's why it's important to eat foods rich in vitamin C, because vitamin C helps the body to build collagen. It's also important to ingest good sources of collagen. You can buy plenty of supplements because generally we don't really eat sources of collagen anymore. You'd have to eat like a lot of organ meats, as well as, bone marrow and things like that. And we tend to stay away from foods like that. We don't really, find them appetizing. And so keep with your vitamin C, as well as taking collagen supplements. And if you can, substitute bone broth for chicken broth and things like that, because bone broth will be high in collagen as well. Fibrous proteins are strand-like and function in structure and support, so collagen would be a fibrous protein. So is keratin, found in your skin, hair, and nails, as well as collagen. Globular proteins are rounded and function as transport proteins, such as hemoglobin, pictured here, enzymes, antibodies, hormones, neurotransmitters, pigments, etc. The complementarity of structure and function is greatly illustrated when we look at proteins. The function of a protein is determined by its structure. Denaturation occurs when the protein is no longer functional as a result of a structural change. So drastic changes in the temperature or pH of a body can disrupt hydrogen bonds within those proteins, causing them to lose their shape. And to end with the comic, running away from your problems does not count as exercise. Oh, well, thank you and have a wonderful rest of your day. Be blessed.